Classical mechanics is the branch of physics used to describe the motion of macroscopic objects. It is the most familiar of the theories of physics. The concepts it covers, such as mass, acceleration, and force, are commonly used and known. The subject is based upon a three-dimensional Euclidean space with fixed axes, called a frame of reference. The point of concurrency of the three axes is known as the origin of the particular space. Classical mechanics utilizes many equations, as well as other mathematical concepts, which relate various physical quantities to one another. These include differential equations, manifolds, Lie groups, and ergodic theory. This page gives a summary of the most important of these. This article lists equations from Newtonian mechanics. See analytical mechanics for the more general formulation of classical mechanics, which includes Lagrangian and Hamiltonian mechanics, classical mechanics, mass and inertia, derived kinematic quantities, derived dynamic quantities, general energy definitions. Every conservative force has a potential energy. By following two principles, one can consistently assign a non-relative value to U wherever the force is zero. Its potential energy is defined to be zero as well. Whenever the force does work, potential energy is lost. Generalized mechanics, kinematics. In the following rotational definitions, the angle can be any angle about the specified axis of rotation. It is customary to use theta, but this does not have to be the polar angle used in polar coordinate systems. The unit axial vector, n, equals E, r, times E, theta. Display style mathbf hat n equals mathbf hat e underscore r times mathbf hat e underscore theta. Closing curly bracket backslash closing curly bracket defines the axis of rotation e r. Display style script style mathbf hat e underscore r backslash closing curly bracket equals unit vector in direction of r e theta. Display style script style mathbf hat e underscore theta backslash closing curly bracket equals unit vector tangential to the angle. Dynamics. Precession. The precession angular speed of a spinning top is given by omega equals W R I omega. Display style bold symbol omega equals frac W R I bold symbol omega, where W is the weight of the spinning flywheel. Energy. The mechanical work done by an external agent on a system is equal to the change in kinetic energy of the system. General work energy theorem. Translation and rotation. The work done W by an external agent which exerts a force F at r, and torque tau on an object along a curved path C is W equals delta T equals C F D R plus tau N D theta. Display style W equals delta T equals int underscore C left. MathBF F C dot mathroom D MathBF R plus bold symbol tau C dot MathBF N mathroom D theta right backslash closing curly bracket, where theta is the angle of rotation about an axis defined by a unit vector n. Kinetic energy. Delta E K equals W equals 1, 2, m, v, 2, minus, v, 0, 2. Display style, delta E underscore K equals W equals frac 1, 2, m, v caret 2, v underscore 0 caret 2. Closing curly bracket. Elastic potential energy. For a stretched spring fixed at one end obeying Hooke's law, delta E P equals 1, 2, K, R, 2, minus R, 1, 2. Display style delta E underscore P equals frac 1, 2, K, R underscore 2, R underscore 1, caret 2, backslash, closing curly bracket, where R2 and R1 are collinear coordinates of the free end of the spring in the direction of the extension, compression, and K is the spring constant. Euler's equations for rigid body dynamics. Euler also worked out analogous laws of motion to those of Newton. See Euler's laws of motion. These extend the scope of Newton's laws to rigid bodies, but are essentially the same as above. A new equation Euler formulated is I alpha plus omega times I omega equals tau. Display style mathbf I c dot bold symbol alpha plus bold symbol omega times left. Mathbf I c dot bold symbol omega right equals bold symbol tau backslash closing curly bracket, where I is the moment of inertia tensor. General planar motion. The previous equations for planar motion can be used here. Corollaries of momentum, angular momentum etc. can immediately follow by applying the above definitions. For any object moving in any path in a plane, r equals r t equals r e caret r. Display style mathbf r equals mathbf r t equals r mathbf hat e underscore r backslash closing curly bracket. The following general results apply to the particle central force motion. For a massive body moving in a central potential due to another object, which depends only on the radial separation between the centers of masses of the two objects, the equation of motion is d 2 d theta 2 1 r plus 1 r equals minus mu r 2 l 2 f r. Display style frac d caret 2 d theta caret 2 left frac 1 mathbf r right plus frac 1 mathbf r equals frac mu mathbf r caret 2 mathbf l caret 2 mathbf f mathbf r. Closing curly bracket. Equations of motion. Constant acceleration. These equations can be used only when acceleration is constant. If acceleration is not constant, then the general calculus equations above must be used. Found by integrating the definitions of position, velocity and acceleration. See above. Galilean frame transforms. For classical Galileo-Newtonian mechanics, the transformation law from one inertial or accelerating, including rotation, frame, reference frame traveling at constant velocity, including 0, to another is the Galilean transform. Unprimed quantities refer to position, velocity and acceleration in one frame F. Primed quantities refer to position, velocity and acceleration in another frame F, moving at translational velocity v or angular velocity omega relative to F. Conversely, F moves at velocity v or omega relative to F. The situation is similar for relative accelerations. Mechanical oscillators SHM, DHM, show, and DHO refer to simple harmonic motion, damped harmonic motion, simple harmonic oscillator and damped harmonic oscillator respectively. See also. Notes. Arnold, Vladimir I, 1989. Mathematical Methods of Classical Mechanics. 2nd ed. Springer. ISBN 978-0-387-96890-2. Berkshire. Frank H. Kibble. T. W. B. 2004. Classical Mechanics. 5th ed. Imperial College Press. ISBN 978-1-86094-435-2. Mayer, Meinhard E. Sussman. Gerard J. Wisdom. Jack. 2001. Structure and Interpretation of Classical Mechanics. MIT Press. ISBN 978-0-262-19455-6.